All right, so are you ready for this? Let's take a deep dive into quantum gravity.
Always ready for those big questions.
It's a physics paper we're looking at today, and it's a doozy.
Oh yeah, what's the title?
Quantum gravity as gravitized quantum theory.
Kitschy? I'm intrigued.
Me too. And it gets even better.
How so?
It basically says quantum gravity isn't just about, like, black holes and the Big Bang.
Which is what we usually think about, right?
Right, it's like the big stuff out there.
Yeah, the really big stuff.
But this paper suggests it's actually even more fundamental than that.
Okay, now you've got my attention.
It's like the fabric of reality on the tiniest levels imaginable.
Wow, so we're talking about the building blocks of the universe here.
Exactly, and it all starts with this problem that's been driving physicists crazy for decades.
Okay, I'm all ears.
It's the cosmological constant.
Ah, yes, the energy of empty space.
Yeah, and quantum mechanics says it should be huge EE.
Right. Empty space should be teeming with energy.
But then when we actually measure it, it's like incredibly small.
It's one of the biggest mysteries in physics.
A total mismatch.
Exactly, and this paper claims to have an answer.
No way! Do they really?
They do. They've come up with a new way to calculate the cosmological constant.
Damn it.
And the result matches what we observe in the universe.
Get out. How is that even possible?
It involves some seriously mind-bending math, but what's really wild is this.
What's that?
It brings together the smallest and largest scales imaginable.
Okay, now you have to explain that one.
So on the one hand, you have the Planck length.
The smallest possible unit of distance.
Yep, tiny, tiny, tiny. And on the other hand, you have the entire observable universe.
Okay, I would never have thought to put those two things together.
And yet this paper manages to connect them in a way that actually makes sense.
So how can something so small tell us anything about the entire universe?
Well, that's where things get really interesting.
Do tell.
They're proposing a whole new way of thinking about space-time itself.
Okay, I'm listening.
Instead of it being this smooth, continuous fabric like we usually imagine.
Yeah, like a blank canvas that everything exists on.
Exactly. This paper suggests space-time might be modular.
Modular, like Lego blocks.
Exactly. Imagine space-time being made up of these tiny little chunks.
Like cosmic Lego bricks?
I like that. Cosmic Lego bricks. And each of these space-time atoms has a kind of hidden twin.
A twin? Hold on, now you're just messing with me.
I know it sounds strange, but hear me out.
Oh.
Think of it like a musical instrument, right? You have a fundamental note,
Okay, I'm with you.
and then you have all those overtones.
Right, the different frequencies that make up the sound.
Exactly. And those overtones, they exist in a different kind of space, right?
Yeah.
But they're still linked to that fundamental note.
That's true.
So this paper suggests that every point in space-time might have a counterpart in this other dual space.
A secret twin.
Exactly. And they're linked in a very specific way.
This is blowing my mind already.
But here's the thing. This dual space, it's not just some mathematical trick.
It's not.
Nope, it has real physical implications.
Okay, now I'm really interested. What kind of implications?
This is where it gets really exciting.
I'm on the edge of my seat.
This dual space could be the source of both dark matter and dark energy.
Wait a minute, are you serious?
I am. That's what they're proposing.
So you're telling me this paper suggests a completely new structure of space-time?
That's right.
And this structure could explain dark matter, A&D, dark energy?
It's a pretty bold claim.
That's huge EE.
That's just the beginning.
There's more.
Oh, yeah. This new structure of space-time, with its dual space and space-time atoms, it leads to some strange consequences.
Okay, like what? I am officially hooked now. Tell me everything. What kind of strange consequences?
Well, for one, it suggests that different observers might see different versions of space-time.
Hold up, what? How is that even possible?
It all depends on their relative motion.
You mean like how fast they're moving relative to each other?
Exactly.
So our experience of space-time, it's not universal, it's relative.
You got it. It's like, imagine you have a sculpture,
Okay, I'm picturing it.
and two people are looking at it from different angles.
They'll see different sides of it, yeah.
Right. So maybe space-time is kind of like that.
Wow, that's trippy.
The paper calls this relative locality.
Relative locality, got it. So it's like we've been looking at the universe through a narrow window this whole time.
And this paper is saying, hey, there's a much bigger picture here.
This is already blowing my mind, and I have a feeling we're just getting started.
Oh, we've got a lot more to unpack. What we've covered so far, that's just the foundation.
So there's even more to this theory.
Oh, yeah, this paper makes some even bolder claims.
Like, what? Don't leave me hanging.
Well, some of these claims could actually be tested in a lab.
Wait, really? We're talking about actual experiments, not just theoretical stuff.
We're talking experiments. And some of them might even be possible with the technology we have right now.
Okay, now you have to tell me more. What kind of experiments are we talking about?
No giant particle colliders or telescopes or anything like that.
Okay, good, because I was picturing like some crazy expensive experiment.
Nope, these could be done in a regular lab.
You're kidding. What would they be looking for in a lab?
It all comes down to how particles interfere.
You mean like the double slit experiment?
Exactly. The one where the particles act like waves.
And create that interference pattern, yes.
That's the one. And remember how weird that is?
It's like the particles go through both slits at the same time, even though they shouldn't be able to.
Exactly. It's like they know they're being watched or something.
Quantum mechanics always messes with my head.
Well, this paper takes that weirdness even further.
How so? How can it get weirder than that?
Imagine we had a third slit.
A triple slit experiment.
So-
Okay, now we're really going down the rabbit hole.
And this triple interference pattern, it's super sensitive
Sensitive to what?
to the underlying structure of space-time itself.
Whoa. Okay, hold on. How does that work?
So remember those tiny space-time atoms we talked about?
Yeah, the cosmic Lego bricks.
If they're real, they should leave a unique fingerprint on that triple interference pattern.
So it's like using particles to probe the very fabric of the universe?
You got it. It's a way to see if space-time is smooth or chunky.
And what would this fingerprint look like? How would we even know if we found it?
That's where the math gets really intense, but
Yeah,
basically
yeah.
the paper lays out the specific calculations for what to look for.
And they actually propose an experimental setup.
They do. They suggest using a diffraction grating and a nonlinear medium.
So shine a beam of light through it and see what happens.
Exactly. And look for those subtle variations in the interference pattern.
Wow, so we could actually have experimental evidence for this modular spacetime idea.
It's a real possibility, and it could happen sooner than we think.
That's incredible. Okay, so back to these spacetime atoms for a second.
Sure, what about them?
You said earlier they might not follow the normal rules of statistics.
Oh, yeah, that's right.
And honestly, statistics isn't my strong suit.
Don't worry about it. This is some next level stuff anyway.
Okay, so in the quantum world, particles are either bosons or fermions, right?
Right, and those determine how they behave in groups.
But these spacetime atoms, they might not fit into either category.
Exactly. It's like they're playing by a whole different set of rules.
Okay, now you're just messing with me.
I'm serious. It's called infinite statistics.
Infinite statistics. Seriously, what does that even mean?
Think of it like this. Remember those cosmic Lego bricks we were talking about?
Yeah, I'm starting to get attached to that analogy.
Imagine a Lego set where you can put an unlimited number of bricks in the same spot.
That's not how Lego works.
Exactly. But that's kind of what infinite statistics implies for these space-time atoms.
So it breaks all the rules we're used to.
Pretty much. It's a whole new ballgame.
This is both amazing and terrifying at the same time, but how could we ever actually observe this?
We might not need to shrink ourselves down to see it.
Because?
Because if this is really how space-time works, it should create specific patterns.
Patterns of what?
Patterns in the fluctuations of space-time itself.
Fluctuations, like ripples in the fabric of space-time.
Exactly. And we might be able to detect those ripples with something like LIGO.
Wait, LIGO, the Gravitational Wave Observatory.
The very same.
You mean the one that detected those colliding black holes?
Yep. And those neutron stars.
So you're saying LIGO might be able to detect the subtle tremors of these space-time atoms.
It's a long shot, but it's definitely a possibility.
So we could literally be listening to the very breath of the universe.
That's the idea. It's pretty wild, right?
Wild doesn't even begin to cover it. This paper is full of incredible ideas. We've gone from dark matter and dark energy to the building blocks of space-time itself.
And we're not done yet. There's still more to unpack.
Seriously, what else could there possibly be? Okay, so we've talked about how this theory could explain some of the biggest mysteries in the universe. Things like dark matter, dark energy. But what about the stuff we see and interact with every day? The particles that make up, well, us.
That's actually one of the most exciting things about this paper. It doesn't just throw out these wild ideas about space-time and then call it a day.
It's more.
It uses this new framework, this gravitized quantum theory, to make specific predictions about the particles we actually observe.
You're saying it can predict the properties of those particles too, like
Right.
their masses.
Precisely. And not just in some vague, hand-wavy way either. This paper lays out specific numerical estimates for the masses of fundamental particles.
Get out of here. And how close are those estimates to what we actually observe?
Surprisingly close.
Wow. Okay, now that is impressive.
Most theories about quantum gravity are so abstract they're practically impossible to test. But this one's making concrete predictions about the universe we can measure and observe.
That's incredible. How do they even begin to do that?
They use these really elegant seesaw-like formulas that basically relate the masses of heavier particles to lighter ones.
Seesaws again. Are we sure these physicists aren't just obsessed with playground equipment?
Maybe, but it's a good analogy. It's like there's this cosmic balancing act going on where the properties of one particle are intertwined with the properties of all the others.
So if one thing changes, everything else has to adjust.
Exactly. It's a beautifully interconnected system, and if these predictions turn out to be correct,
It must be a huge win for this theory.
right, absolutely. Finding experimental evidence to back up those predictions would be a major breakthrough in our understanding of, well, everything.
Quantum mechanics, gravity, the whole shebang.
The whole shebang.
Wow, okay, so let me get this straight. This paper is suggesting a whole new picture of reality where space-time is made of these tiny, interconnected space-time atoms.
Right, like a cosmic Lego set.
And these atoms, they hold the key to understanding the biggest mysteries in the universe, from dark matter and dark energy to the particles that make up you and me.
It's like we've been looking at the universe through this blurry lens, and this paper is giving us a chance to finally see it in high definition.
And the best part is, it's not just some crazy idea that's impossible to prove or disprove. We might actually be able to test it.
Exactly, and that's what makes science so exciting. Even the most radical ideas can be explored, tested, and either confirmed or refuted by what we observe.
And who knows what other incredible discoveries await us? It feels like we're standing at the edge of a new era in physics where anything is possible.
It's an amazing time to be thinking about these questions, and this paper is a perfect example of that. It reminds us that the universe is a far stranger, more wondrous place than we ever imagined.
I love these deep dives. They always leave me feeling inspired and a little bit mind blown. Thanks for joining us on this journey into the world of quantum gravity.
My pleasure, and who knows what other mysteries we'll uncover together in the future.
That's right. We'll see you next time for another deep dive into the world of cutting edge science. Until then, keep exploring, keep asking those big questions, and most importantly, never stop being curious about the universe and our place in it.